Okay, hello everyone to today's seminar on interval methods in control engineering. It's my great pleasure to introduce Etienne Bertin today. And Etienne did his master studies at ENSTA Paris and the University of Paris-Saclay. And yes, since some time, he's now a PhD student at the French Aerospace Institute Honoraire at the same time at ENSTA Paris, where he's supervised among others, by Alexandre Chapoutot and Julien Alexandre Di Sondrato. And now I think it's time to hand over the microphone to you, Etienne. And yes, your talk will be about enclosing optimal trajectories using spatio-temporal constraint zonotopes. We're looking forward to your presentation.
Okay. So good afternoon, everyone. So we work in a robust optimal control, and we try to enclose optimal trajectories using spatio-temporal constraint zonotopes. And it's a combined work of ENSTA and ENSTA. So if we want to design a reusable launcher, we're faced with a control problem with very strict constraints. So we need the trajectory to end on the landing pad with a null velocity, else the vehicle will crash, which is pretty big issue. So in this situation, we want a controller that is robust, that is to say that it is guaranteed to bring the vehicle to its destination, despite errors that may be done during on flight. So gaining a launch vehicle can be formulated as an optimal control problem. So we have a system with state Y that follows a dynamic F, which depends on the control, which is a function chosen such that it brings the system from an initial state to a final state while minimizing a cost, which could be like fuel consumption. So also we are working on aerospace problem. The scope of optimal control problems that we consider is much larger, like anything that can be written in this form. So such a problem can be solved. It will yield a trajectory such as this one, but this trajectory will not exactly correspond to the actual trajectory of the launcher because our model is not exact. Notably, it depends on parameters like the engine thrust or aerodynamic coefficients that are not well known in practice. And also, the initial state of the system might be subject to uncertainties, especially when doing a re-entry problem because our initial state is in the middle of the air. So we'll assume that the uncertainties are bounded. That is to say that the parameters and initial state take their value in bounded sets. And under this assumption, we'll have a dynamics with uncertainties, where at any given time, there is a set of possible state and a set of possible dynamics. So instead of having a single trajectory, we'll have a tube of possible trajectories like the orange set here. Our goal is to enclose this orange set to assess whether there is a risk of entering an unsafe state like this one. So the first difficulty we'll encounter will be this control here because it's a function. It's an unknown that is a function. So it's an infinite dimensional function. So the first thing we will do is characterize the optimal trajectories in a way that it abstracts the controls away. And then we'll enclose the optimal trajectories using validated methods, which will tweak with spatio-temporal zonotopes. And then we'll apply our optimality constraints on the trajectories we just enclosed in order to have a validated enclosure of optimal trajectories at the end. So first, let's get rid of that infinite dimension control. So there's a school of optimal control called the indirect optimal control that can characterize that will use the optimality necessary condition of optimality to abstract. So for this, we'll use the Pontryagin maximum principle, which states that if a trajectory and a control are optimal, then there exist other coordinates called the costate, P here, that follows a dynamic of its own. And when we know the state and the costate, we can determine the control by minimizing a function that's called the state and the costate. Then it follows a non-controlled dynamic because we can replace the variable u by argmin of h. So this system will have a boundary constraint of its own. So basically we have a system with degrees of freedom at the beginning. So like most notably the initial costate is a degree of freedom, even degree of freedom, and we have constraints at the end. So we end up with an initial value problem where we have to find the initial value of the costate, such that when we integrate this system, at the end we satisfy the constraints. However, this system isn't easy to simulate because there is an argmin here, which will create hybrid dynamics. So let's look at this on a simple example. So take a double integrator that wants to go from this height to this height in minimum time. So we have a position r. Its derivative is the velocity. The derivative of the velocity is the control times the parameter. So this parameter would typically be a reactor thrust of some kind. We have boundary constraints. So we start here with a null velocity, and we want to finish here with a null velocity. And we want to do this in minimal time, so we want to minimize the integral of 1. So when we apply the PMP on this problem, so we get a costate with two coordinates, PR and PV. They follow this dynamic, which again is obtained by is given by the PMP. This dynamic means that PV is an affine function, and the control is defined at any time as minimizing the Hamiltonian, which is this function. And so, because this minimization leads to this value. So either u is equal to -1 if PV is positive, or u is equal to 1 if PV is negative. So all of this information means that we'll have a costate that will look like this. It will be an affine function with the degrees of freedom are its initial value and its slope, because PR is the slope of this function. When this is positive, the control is equal to -1. When this is negative, the control is equal to 1. So basically, we have a transition from -1, an abrupt transition from -1 to 1 when PV crosses 0. And this will lead to a trajectory that looks like this. So where we have basically we have a falling ball that takes up until PV crosses 0, and then we have like a falling ball but in reverse afterward. So this is the kind of information you can get with the PMP. And like since here we have an abrupt transition from control -1 to control 1 here, what we'll do is we'll simulate up to this time with the dynamic when u is equal to -1, and then we'll simulate from this time to this time with the dynamic when u is equal to 1. And so instead of having a hybrid dynamic, we'll have a switch system where we have one dynamic up to time θ1, where θ1 which is defined as when PV is equal to 0, and then we'll have another dynamic after between θ1 and θ2, which will be the final time. So, so for the sake of this presentation, when we'll use this system again, instead of using this event, the event when PV is equal to 0 as the definition of θ1, we'll use the event when R is equal to 0. So, once we've done all this analysis, what this means is that basically we found the optimal trajectory structure. So we put it as a switch system with constraints. So we have a set of switch time θn's. In between switch times, we follow continuous dynamic that we can simulate. And at switch time, we have to satisfy constraints, which is to be here, which is to be r equal to 0, for instance. And here we have r equal to -1. So at the end of the day, so we have initial value problem with multiple boundary constraints that apply at different time. So we still have, but it's still a problem with degrees of freedom, so the initial cause state and transition time, and we have to find the value of this variable such that when we integrate this system, we satisfy all these boundary constraints, but boundary constraints that apply at each transition time. So this is the problem that we'll consider throughout this presentation, and we'll try to enclose all of its solutions. And for this, we'll use validity methods. So the principle of validity method is to enclose the results in sets rather than approximate them with floating point numbers. So for instance, P could be enclosed in this interval. To use these sets, any real function is replaced with a set-valued function that satisfies the inclusion principle. Noting that will not with bracket any function that satisfies this principle, even if it's Zonotop valued. And speaking of Zonotopes, so there are multiple sets that this function can use. So on one side of the spectrum, we have interval vectors, which are very cheap, but their rectangular shape induces a significant over-approximation. Then on the other hand, we have polytopes, which are very precise, but much more expensive. And then we have zonotopes, which thanks to the generator representation, manage to be quite cheap and quite precise at the same time. So in our work, we use Zonotop, and we also use another representation, which are constraint Zonotopes, which has Zonotop with additional linear constraints. And I will dive a little deeper in constraint Zonotopes. So while the Zonotop is defined as a affine transformation of a box, so we have a box of noise symbol, which is -1 times d epsilon, and we multiply it by a matrix X plus a center X hat, and we get this Zonotop here. Like noting that the noise symbol is typically in a larger dimension than the Zonotop, which is in our coordinate space. So, so this is a Zonotop, and when to get a constraint Zonotop, we'll add constraints, linear constraints on the noise symbol box. So to define a constraint Zonotop, we'll have an additional matrix, a constraint matrix A, and we'll add that the noise symbol is in this box and satisfies this linear constraint here. So this means that we take this box, we intersect it with a plane, we get the red part here, and when we do an affine transformation with matrix X, we'll get this red set here, which can be potentially as precise as a polytop. So this representation is useful is particularly useful for sets that are defined as satisfying constraints. So, for instance, let's take the zonotope X, and let's take a constraint function C. If we want to enclose this set, so the set of elements of the zonotope that also satisfy these constraints, C of X is equal to 0, then this set is enclosed in the zonotope X of A, where A is a zonotope evaluation of C. And I think it's interesting to see how it works. So basically, we just use the principle of symbolic zonotopes, which states that there is a value of the noise symbols such that every zonotope is equal to the variable it encloses. That is to say that if I want to take any x in the zonotope X, then there exists a realization of the noise symbol epsilon, such that x is equal to matrix x, big X times epsilon plus x hat, and C of x is equal to A to big A times epsilon plus A hat, because A is the zonotope that encloses C of x. So this means that if we take x in this set, so x that satisfies C of x is equal to 0, there exists a noise symbol such that x of times epsilon is equal to x, and A times epsilon is equal to 0, which literally means that x here belongs to the constraint zonotope X of A. So this is a proof when we use symbolic zonotope, but even if you don't use symbolic zonotope, you can use constraint zonotope with lifted zonotope like this one. I advise you to look at Scott and Al article. So the constraint zonotopes have one drawback, however, they are a partly implicit representation, because we have linear constraints on our noise symbols. So if you want to an explicit representation of a zonotope, of a constraint zonotope, one way to do it for cheap is to solve a set of linear problems. So say I want to enclose this red constraint zonotope. I will choose a direction. I will solve this linear problem to see how far in this direction the constraint zonotope goes. This gives me a bounding plane, and can do this for multiple directions. I will start to get a side of a polyhedron, and if I do it all the way, I will get a conservative enclosure of. I get a polyhedron, polytope rather, that conservatively enclose my constraint zonotope, like this here. So to sum up, we use constraint zonotope because they allow for a straightforward representation of this kind of sets, which is exactly what we the kind of set we want to enclose with our optimality conditions. Because it can be easily embedded in the zonotope-based algorithm, because all we need is affine arithmetics to compute the constraint part, because it's a regular zonotope. However, the big drawback is that if we want to express explicitly our zonotope, we'll need to solve several linear problems. But that's not so much of an issue for us, because we don't need to an explicit representation of our constraint zonotope during our computations. We just need a zonotope held like this one. So that was a digression on constraint zonotopes. But the other validity method we'll use for this is validity simulation. So validity simulation will enclose all possible trajectories of dynamics with uncertainties in a sequence of Picard box here and zonotopes in blue here. So it's convenient to enclose like if we want to simulate a set of system over a common duration. However, it's not straightforward. The application is not straightforward in our case because we don't want to enclose the trajectories between two times, but rather we want to between the time 0 and time 8h, but rather we want to enclose the system between time 0 and the time where it reaches this line here. Because remember, we have a problem that where we have boundary constraints that we want to apply when it reaches this line, and it will change its dynamic when it reaches this line. So we want to enclose the system when it reaches this line. So there are multiple solutions, methods that exist in the literature to do this, notably methods that rely on discretizing time, on discretizing the time here, and taking a union of sets that will enclose this part here. But we'll propose another approach that will be more convenient for us because we'll need to apply constraints afterward. And this approach will enclose all these events in a single Zonotope. And for this, we'll build a spatio-temporal Zonotope. So, oh wait, I didn't realize that I have this right now. Okay, sorry about this. We'll build a spatio-temporal Zonotopes. So it will work a little like a validity simulation. So we'll start with an enclosure of all our trajectories at time 0. We'll deduce a Picard box that will enclose all our trajectories over time over duration 0h. Then we'll enclose the dynamics f and the subsequent derivatives of f over this duration using this box. And then we'll apply a validated Taylor interpolation to get to the Zonotopes that encloses on trajectories. Except we'll do a small change compared to regular validity simulation, is that instead of just enclosing the trajectories at time h, we'll build a Zonotope with a time coordinate that will enclose our trajectories over the entire duration 0h, like this one here. This will be convenient to this will be convenient because say we have so I get back to our system that change dynamic when it reaches 0 here. So say I have an enclosure of the time at which the system crosses this line. I will get back to this later, to how I get this later. So I have an enclosure of this time, so I can take h is equal to the width of this interval. This gives me first spatio-temporal Zonotope. I can simulate it up until then. Then I get this Zonotope dotted here, and this Zonotope encloses the system during the entire duration during which the event is possible. Right? So, and because it encloses the system during the entire duration during which it's even possible, it notably increases the system at time theta. So we can then apply our optimality condition C of x of theta equal to 0 on this Zonotope using the constrained Zonotope formalism, and we get this constrained Zonotope, which encloses our system at the time where it reaches 0. So that's the first brick we need to enclose our optimal condition, our optimal trajectories, rather. So we had our system, we are a switch system with constraints that apply at time θn, and we have a way to apply or to enclose our system at time θn and apply our constraints. But there are two things missing here. First, we needed, to do all of this, we needed a prior knowledge of an enclosure of our switch time theta. And second, like it's not enough to have an enclosure at time theta. We want to have an enclosure of optimal trajectories at any time, and notably at the initial time. So to complement our method, we'll propagate our constraint backward and embed all of this in an inflating construct to have a validated enclosure of our trajectories. And the first, we propagate our constraint backward. So for this, we'll start with some notation. So consider that the function that takes an initial co-state and transition time, consider a function that will take these variables, then simulate this system. So this is the system that is equivalent to our optimal trajectories. So it simulates this system, and then it outputs the state and co-state at time 2. Well, if we have this function, so I call it the flow phi. With this function, I can rewrite my initial value problem as find P0 and theta such that this function, the boundary constraints composed with the flow, is equal to 0. So this is a mathematical framework to propagate my boundary constraints backward to time 0. And well, so this is a function, and we'll try to make a validated Taylor approximation, not approximation, a validated Taylor enclosure at offered 0. So that is to say, so consider that f is equal to this. We want to build this function. And for this, we need an enclosure of the gradient of f. So the gradient of function c is easy because the constraint function c is typically like an explicit form function. So we just need to derive it, to differentiate it. But however, we need the derivative of the flow, and this can be obtained by using a dynamic systems theory. Indeed, the derivative of the flow is equal to the resolvent matrix, which is solution of the system. This system is obtained basically by derivating this system corresponds to linearizing the dynamics around a trajectory. Right. So if we simulate this system with validated simulation, we'll get an enclosure of the derivative of the flow. So with an enclosure of the derivative of the flow, we can compose it with our validated Taylor, and we'll get an inclusion function for our function c of Cn composed with phi. When we have this inclusion function, we can then compute the constraint zonotop x of a, where x is an enclosure of one of our variables. So, for instance, our initial co-state or transition time theta, and a is equal to the zonotop evaluation of this inclusion function composed with x. So this is a way to propagate our boundary constraints backward to time 0. And this will allow us to build an inflated contract method to enclose all the variables of our problem. Indeed, let's start by solving our optimal control problem for some values of the parameters. So this will give us a point cloud in a range like this. Then we want to have the solution for all values of the parameters. So we start with a box that encloses our point cloud. So this will be like our a priori enclosure of our variables. So we'll input this into our program. So our program will transform this box into a zonotop. It will it will propagate all the optimality constraint backward on this zonotope, and we'll get a constraint zonotope, which is right here. Now, if our constraint zonotope touches the edge of our box, that means that there might be some solutions, some optimal values on the other side. So what we do is that we inflate the box, and we inflate it again until the entire set of possible solutions is in the entire of the set, is strictly included in this set. When this is the case, we are guaranteed to have all the possible solutions. And then we contract this box with fixed point iteration. Sorry. So this inflate and contract methods allows us to have a validity enclosure of all our degrees of freedom. So so we have the guaranteed enclosure of our initial cause state and our transition time. And if we have a guaranteed enclosure of our transition time and our initial cause state, then we can deduce an optimal guaranteed enclosure of the optimal trajectories with our validated simulation and backward propagation of boundary constraints. So we have a self-contained method. And we apply this method to a simple aerospace problem. So take a vertical Godard problem. So I have a launcher with position R. Its derivative is velocity. Derivative of velocity is a non-linear gravity field plus the reactor thrust, which is controlled, variable u here. And derivative of the mass is the fuel consumption. We want to go from this altitude to this altitude while using as little fuel as possible. So we solve this problem for multiple values of the parameters using this gives us the orange trajectories here. And then we solved it with our algorithm, will give us the blue enclosure here. And the blue set we obtain, so the blue constraints on top here, enclosed the orange trajectories, so trajectories for multiple values of the parameters. And the over approximation was either like not too big. So to sum up, what we did. So we started with an optimal control problem, and we wanted to enclose the optimal trajectories. We transformed this optimal control problem into an uncontrolled switch system using optimal indirect optimal control theory. So we enclosed the trajectories of this uncontrolled switch system, and we dealt with variable switch time using with spatio-temporal zonotopes that enclosed the entire duration during which an event was possible. We added our boundary optimality conditions as constraints on these zonotopes using constraint zonotope formalism. And we propagated this constraint backward using validated linearization of the dynamics. And we embedded all of this into an inflate and contract method to have a guaranteed bounds on our variables which yielded a guaranteed enclosure of our optimal trajectories of our problem. So, in the future, we work on applying this method to more complex aerospace problems. So, for instance, our goal is to apply this to a multidimensional re-entry problem, like the one I presented at the beginning. And we're also working on decreasing the over approximation by using better geometry for our spatio-temporal zonotopes. Thank you for your attention, and do you have questions?
Okay, many thanks for a very interesting presentation. And yes, I'll just follow your question at the end. Is there anything someone wants to ask?
Hi, hello. Yes, I have a question.
Yes, please go ahead.
Hi, hi. My name is Xue, and I'm a postdoc in the University of Normandy, in France. So I'm glad to be here and listen your presentation. And I have a question in the page in the 3. So in the resource part, yes.
This one?
No, next one, 23 then.
Okay.
No, there is one, no, maybe 22, you have some animations. I'm
No, this one.
wondering how, yeah, this one, yes. Yeah, this one in the 21, 24. I'm wondering how you choose these fixed point iterations. So the time to choose these iterations, how do you choose it?
How do I what you said?
You write here the contract box with fixed point iterations. So how do you know the number of these fixed point iterations?
As a number, how many do I do?
Yes.
Okay. Basically, I do them until two until two consecutive blocks are too close from one another, and I consider that the gain of precision isn't worth it anymore. Like for instance, here you see, so my constraint on the top goes up to there. So
Yes.
my next box, right? My next box, you can see the next box basically has the same bound, like the bound of the box. And like you can see here, like my set hasn't changed much between these two iterations.
Yes.
So I stop soon afterward.
Okay. So that means you have a minimum value, and when you reach this value, and you stop the iteration. That is.
Yeah. Like
okay.
if the volume of box n plus 1 is
Yes.
equal to the same volume as box n within like I guess
A small value.
1%. Like if there is less than a 1% gain of
Yes.
volume, I stop the algorithm.
Okay. Got it. Thank you.
Okay, now I think Luc has raised his hand.
Yes, thank
Please
you.
go ahead with your question.
Can you hear me?
Yep.
Yes.
Okay, good. So my question was about how to compute the envelope, the Zonoton envelope, because here you have a differential inclusion.
Yep.
You have some uncertainty, and I did not catch how you are able to enclose in the case where, so you do not assume that you know the derivative for xi.
No. Oh, right. I do. Xi is constant. It's fixed.
Okay, so maybe it was written somewhere. Okay. So the second question is how, because the fact that it is constant is maybe in some cases it is not the case. How you can, do you think you can extend your approach in the case where xi is not constant?
Well, because of the way validity simulation handles this computation, we can assume that the parameter is like constant par morceau.
Piecewise constant.
Piecewise constant, like. But in the case where it changes, yeah, I'm not sure. Like, it's one of the questions I'm wondering in my thesis. I guess we need like there are many cases where like you can like the boundary trajectories correspond to the trajectories with the maximum values of the parameters. So in this case, it doesn't really matter whether the parameters vary or not. But in the general case, I'm not quite. I'm not sure. Like
Okay.
I won't say anything because I'm not sure.
Okay, thank you. Perfect. Thank you.
Let me just continue with this point. I think the thing that you just discussed with the maximum values represent the enclosure directly, I think this would mean that you also have to check the monotonicity or cooperativity of the state equations. That's one thing. But going back to Luc's question, I think we have to really carefully look again at the formulation of the maximum principle that you had at the beginning. I think it was slide 6 or 7.
Mm-hmm.
Yes, it is here. The thing that you wrote down here is you have the Hamiltonian function h that you're minimizing. You're minimizing this by a suitable choice of the control input. And the control input typically is a function of the states and co-states. And the thing that you described here, using, for example, the first order derivative of the Hamiltonian with respect to u, and setting this equal to 0, and in the minimum time problem, you end up with several piecewise constant solutions. This only works perfectly in the case that your system is linear, and that your Hamiltonian also depends at the end linearly on u, and that you don't have any bilinear couplings between the state y and the input u. In this case, I think that's a very well-known theorem from Feldbaum. I think it even dates back to the 1940s or something like that, where he derived the maximum number of switchings that you can have. In the case that your system model is linear, and you have a system matrix A that only has purely real eigenvalues, then it is known that the maximum number of switchings of a piecewise constant input is limited by the number of states minus 1. That's directly an upper bound for the number of switchings that you can have. In the case that you have multiplicative couplings between u and y, for example, if you have input-affine actuator dynamics, this is unfortunately no longer true. And this can also happen, for example, in cases where you have not minimum time problems, but for example, fuel optimal problems. That means you want to minimize directly a temporal integral over the control input u. And in such a case, I think Luc's question is really very interesting, because what you would end up then is you have either the solution that the partial derivative of h with respect to u becomes equal to 0. That's one candidate. And typically there are also other candidates in which the Hamiltonian, a suitable choice of u, becomes independent of the control input, or maybe becomes constant over a finite time duration. And in this finite time duration, you may have a singular arc of the control. And this singular arc would mean that you have to compute also the second order derivative of h with respect to u, or the third order or fourth order derivative, until you end up at some point with an input dependency. And that's really something that makes your approach, I think, only directly applicable. Maybe you can correct me, but I think your approach is only directly applicable in cases where you can, just by system analysis or by system theory, rule out a singular arc of the control. And in cases where you have a singular arc, I think it doesn't work anymore.
Well, I haven't done a singular arc yet because I've run into difficulties with software. But I think it's possible because, like, even when you have a singular arc, you can often have end up with an explicit definition of the control. Like the formula gets more complicated, but it's possible to have an explicit formulation. And
parameters are not necessarily piecewise constant anymore.
I mean for the what do you mean? Like
I think what you will have at the end is you have some formula, maybe very complicated, u depending on states and co-states. That's something you will have. But this free parameters, the vector psi that you have at the end, that you want to optimize, that parameterize also your optimal control strategy. There will be some of those parameters included also in the singular arc, and they may be time-dependent functions. And this is really something, you will get a solution at the end, that's true. You're gridding the time horizon maybe in piecewise constant parameter values. You're searching for the solution, but I think this will not be the global optimum that you find at the end. It will be just an approximation to this.
Okay, yeah. Okay, so I understand. Yes, because like if we apply optimal control theory to the parameters, so we find the parameters that will like be the more annoying possible. It can have a singular arc that can be expressed with a piecewise. I agree.
Yes, and let me continue with the singular arc. Maybe you want even to remove it. And I think there's a very simple trick that works in practically, let's say, most of those systems where you have input-affine couplings between you and the states. You can just add in the cost function a small quadratic term in the control inputs. If you just say, okay, let's take, for example, minimum time problem. That means you have the integral over the value 1 with respect to t, where the upper bound tf is free. And if you just add plus some 10 to the minus 5 or something 10 to the minus 6 times the control input u square in the cost function, then you directly remove the singular arc. And more or less this solution is something, it's just smoothing out in many problems, is the switching between the singular to the non-singular arc. And that's something I think would partially resolve the problem that Luc started to raise at the beginning, where you have some time varying inputs. And yes, then you end up again with something that is really well behaved.
So yeah, but in this case, we'll need to add a penalty term, but on
you
the
have some small penalty term in the cost function. If you go back to the slide, I think it was the previous one, 7 or 8. Yes, here. No, the next one, the 8. In the red box, you have the integral 1 dt. And if you just say 1 plus 10 to the minus 6 times u square dt, then you already have removed the singular arc.
Yeah, but like singular arc of the control isn't too problematic, because like as long as I have a formulation, or I can simulate it. But it's like rather the parameter. Like if you wanted to work with non-constant parameters, then I guess maybe we can apply the same trick. It's a bit weird to add a cost on the parameter variation.
One thing for my further understanding, if you look at, I think it was the slide number 22, where you had the formulation of Godard's problem.
Yes.
Okay, if you count the number of boundary conditions on your slide, you have only 4 boundary conditions, but you have 6 state variables. That means 3 states and 3 co-states. What is, for example, with the initial velocity? What did you do there? Did you leave it free and represent it by some corresponding constraint on the co-state? Or what did you do, for example, with v at the point of time t0?
What did I do with v?
Yes, because if I just count, you have 4 boundary values, but at the end you have 6 states.
Okay, I have the same number of constraints and degrees of freedom in this problem. So I think, so my constraints, I need to have a final position. So I have a constraint on the final position.
Yes, that's the R of TF.
Yep.
You leave the final velocity and final mass free. That means V of TF and M of TF, they are unbounded. This translates into terminal constraints for the co-states. That means the co-state, the second and third co-state at the end must be equal to 0.
Yes.
Okay, and you have an initial condition for the position.
Yes.
Okay,
Yeah.
now I understand. This y of 0 is not only the position r, it's the full 3-component state vector at the beginning.
Yep, exactly.
Okay. Okay.
And the other degree of freedom in here is θ1. So it's I think I forgot to talk about the control trajectory, but Godard problem starts by full throttle phase and finishes by a free fall phase. Yeah. And θ1 is the end of the full throttle phase, and it has to satisfy a constraints, and which is there is a certain switching function that must be equal to 0 at time θ1. And
yes, it was my fault here. I just forgot that y is the vector composed of r, v, and m.
Yeah. Okay.
Okay.
Problem.
Okay, then we have really 6 boundary conditions.
Yep.
Okay, and then, yes, I would like to continue a little bit with the question that Xu already asked on the slide 21.
Yep.
I think you only answered the question partially. What you answered is you already have one of those blue or red boxes.
Yep.
And you're performing the iteration and find something in the interior. And yes, if you have found something like this, you're sure that yes, the solution will be contained in this box.
Yes.
Okay, the question is where to locate the box, or what is the meaning of your yellow stars? Maybe you said it, but maybe you have been too quick, or I haven't been attentive.
Okay, so if I take my Godard problem and I take some values of the parameters. So for instance, like I'm a stress vector, I take one value in the uncertainty box. So this gives me a numerical set. This gives me a numerical problem because I didn't take the uncertainties into account here, or rather I did, but I just took one values and not all of them. So if I take the system for a set values of the parameters, I can solve it using numerical methods. And that will give me one of this cross here. And I do this for several values of the parameters, and each time it will give me like for each set of values of the parameter, I will solve the problem, compute the optimal trajectories, and find the initial cause state and the transition times. Okay, so that's what
yellow
these
stars are not necessarily some verified initial conditions. They are just numerical guesses, for example, obtained from a classical boundary value problem solver, just using BVP4C from MATLAB, for example, get an approximation for the initial cause states, and then afterwards you build a box around it and search whether this is then being done in a verified way. Then you're searching whether this box is being contracting or not.
Yep.
Okay. And then I got it. Okay.
Okay. Like at the end, you can see that it encloses all the guesses.
Yes, because my question was just where to get those yellow stars from.
Yeah, from a classic numerical solver. So I use a software developed by Onera, which does multiple shooting.
Yes.
It's a shooting method, basically.
Yes, that's a classical floating point-based multiple shooting approach, and you're building a box around it. Okay, now let's see. Do we have any further questions in the audience? Yes, we have a question from Carlos.
Hi, do you hear me well?
Oh, don't quite hear you there.
Okay, it's too low?
Yes, it's a little bit too low.
Okay, but how about now? Is it better?
Much better.
Okay, perfect. Thank you for very nice talking. I have never used a projectile or a missile trajectory or something like that, and see this kind of application is always something really nice. And okay, my question is, I want to say just some comment. First, there is one slide when you show the different representations of the sets, and you just said to present the constraint sonotope like another set, and this is not true. Actually, a polytope and a constraint sonotope is the same. And so you should put it in the next one, like an example. You can represent any polytope. It's just a different representation. And so based on that, why? If you at the end, if I enclose well, if you at the end are enclosing everything in a sonotope, why did you matter into use a constrained representation? Why don't you use just sonotopes? Are much easier. And so you just can represent them by that. I don't see the why have you changed to constrain sonotope when you are at the end enclosing only in a normal regular sonotope. So because I think that the most of the interesting, by the way, I'm not very fan of constrained sonotopes. I think that's another topic to discuss. But if you are using a sonotope for enclosing, to me, it doesn't have a sense to use a constrained representation because now you are adding more constraint that you are not actually using. So it's just going to be a little more complex for nothing, in my opinion. And I didn't get also 21, but I see now it's more clear. So that should be all from my side. And yeah.
Okay. So the reason we use the constraints on top is because so we have this problem here. So we have boundary constraints, right? So we have sets that are defined as satisfying these constraints. So if I go back to here, right? Okay. So normally I will need to take the intersection between this zonotope and this line, right? Because this line is a set that are that satisfy my constraints, and this is the zonotopes that encloses my trajectories. So I have to take the intersection between these two sets somewhat, and some way. So I know there are multiple ways to do this. So I see in literature algorithm to take the to compute the integration, like the intersection of this, to compute the zonotopes that will enclose the intersection between this set and this zonotope. But I find it much more convenient to use constraints zonotop because I don't need any additional software to do this. I can just I just need to compute a zonotop. I just need to compute C of x, so my constraint function on this zonotop here, and I'm done. So really, the reason I use constraint zonotop is because there were a convenient way to handle this issue, which allows me to, and because I didn't need any additional.
Yes, I got it. And usually we have like I wanna try this one to see how they look like, but I don't know, and this is my opinion. I'm not a specialist in missiles and everything, but I would highly suggest try to use a sonotope because it's the same formulation minus the constraint section that you are not using. So it's going to be much simpler. I think maybe could even give you a better computational time or something like that regarding the CPU time. But looks really awesome. So thank you.
I didn't forget what you said. Sorry.
Okay, so that maybe you should try to use a sonotope because you are using just sonotopes. I mean, you are using sonotope represented as constrained sonotope. It means that you are adding additional constraints that you are not using. So regarding the computational time, it's going to be a little bit faster because now you don't have this constraint, this new constraint, the hx equal to some variable. This section you won't have it. You only will have the generator section plus the center. So it's going to be the same representation, but I think it's going to be faster for that because you are not using like a different constraint. I mean, at the end you are using this regular sonotope. So just try it with that one. Maybe it could help you to improve the computational time and so on.
Actually, so I implemented my own constraints on top in the index, and they don't increase the computation time because like I just take the constraint Zonotope and I take it and I take it as a separate Zonotope, and I don't run it through Validity Simulation. So basically, so I have a system which is in dimension like 10 or something. I simulate it up until boundary time. So then I apply my constraints. So I compute a Zonotope evaluation of an inclusion function of my constraints. And this Zonotope, I don't add it to my system. I just to my Zonotope variable. I just store it somewhere, and I just use it when I want to compute the explicit formula of my constraint Zonotope. Well, I guess what I mean is
okay, perfect.
I do my computation with the hull rather than the constraint part, so the constraints don't really don't increase the computation time of validated simulation. Right?
Maybe let me add something to this point, and that's some kind of advertisement for the 25th of February. Because the speaker at the end of February will be Brenner Santano Rego, and I think he's one of the co-authors from the paper that you quoted in this work, and he did a lot of work, was also published recently in Automatica, where he worked on constrained sonotopes for state estimation purposes, also for descriptor systems. And that's just an advertisement. We'll have his presentation at the end of February. Okay, do we have any further questions concerning today's presentation of Etienne? I think this doesn't seem to be the case. Yes, you have already been very patient, I think, answering questions for almost half an hour now. And thanks again for a very interesting presentation, and also thanks for clarifying all the questions. And from that point of view, yes, all of you have a nice Friday afternoon, weekend, and see you again soon. See you again soon means Friday in 2 weeks. We have our last seminar before Christmas, and our speaker then before Christmas will be Nathalie Revol. And see you soon. Have a nice weekend.